During the keynote presentation, Professor Saman Amarasinghe mentioned that tensor operations can be optimized and the total computation time can be heavily reduced by introducing novel custom hardware. Following the same idea, in this work, we are accelerating sparse MTTKRP for tensor decomposition on FPGA. This work is collaborated between FPGA Parallel Computing Lab of University of Southern California and DEVCOM, US Army Research Lab. A tensor can be seen as a generalization of an array in multiple dimensions. A 1D tensor can be seen as an array, and a 2D tensor can be seen as a matrix. Following that, a 3D tensor as a cube, and we can expand this idea into higher dimensions as well. In this presentation, we are focusing on 3D tensors for demonstration purposes. And the tensors that we are considering are sparse in general because the data sets in real world are sparse. Canonical polyadic tensor decomposition. It can be seen as an approximation of an original tensor as a sum of rank 1 tensors. So in here, in this figure, we have shown a 3-mode tensor where we decompose into 3 rank 1 tensors. And at the end, we concatenate all of the rank 1 tensors along each of the mode, which finally output 3 matrices along each mode. Canonical polyadic tensor decomposition can be calculated using different methods, and alternating least square method is the most popular and efficient one used in the literature. Alternative least square method is nothing but performing sparse MTTKRP operation along each of the mode iteratively following a normalization step. Here, the most expensive computation is MTTKRP, and that computation required to be computed along every mode of the input tensor. In this example, I have shown the spMTTKRP operation for mode 0 of a 3D tensor. Here, when we look at the computation, let's say we have the external memory and a compute device. First, we have to load a non-zero tensor element into the compute device. And in step 2, we have to look at this sparse, we have to look at this non-zero element and identify what are the rows of factor matrices that we need to load into the compute device for the computation. So in step 2 and 3, we need to load them and perform element-wise computations between these rows in step 4. Thereafter, we have to take that non-zero element that we loaded from the tensor and then using that and multiply that value with the element-wise product that we calculated in step 4. Finally, we have to load a corresponding factor matrix row, let's say from an output factor matrix, and then update the corresponding row and store it back. The challenges that we have with this computation is if there are multiple compute elements that update in the same row, then there can be a data conflict. So we need to avoid these data conflicts to get a higher performance. Otherwise, we have to go through some locking mechanism or our final outcome going to be incorrect. The second thing is when we do these computations, if we decide to store them, store the intermediate values in the external memory, and then finally add them together in the end, there can be memory explosion due to the size of these intermediate values. So typically this size, typically the memory devices don't have this much of space. So this is not a viable solution as well. So in our work, we introduced the idea of on-the-fly tensor remapping. So the main challenge that we have is to introduce optimizations along each of the modes because MTTKRP required to be computed along each of the modes. But if we have a tensor, if we need to have tensor that have optimizations along each mode, in a typical approach, we may need multiple copies where uh, each of the copy is optimized for a single mode. But then there can be copies proportional to the number of modes. So as the number of modes increases, this is not a viable solution. So what we are proposing is optimizing the computation and external memory access for each mode. But since computation going to happen mode by mode, while performing sparse MTTKRP computation for a mode, we are preparing the tensor for the next mode by remapping the non-zero elements optimized towards the upcoming tensor mode. If we do that, the external memory space that we require is 2 times the size of the tensor, instead of having number of tensor copies proportional to number of modes. So we can have a constant factor of copies and perform tensor decomposition for a large mode tensor. And to support this, we introduced the FLYCOO tensor format. Due to the constraint of time, we are not going into details of how to generate this format. But the idea of FLYCOO is to support this on-the-fly tensor remapping, having pointer values to support the remapping idea, and avoid the intermediate values being communicated to the FPGA external memory by introducing the optimizations while generating the format, and also support distribute the computations among multiple processing elements without having any locking mechanisms, so we can efficiently uh, do the computation and also explore the locality of FPGA external memory accesses. After generating the FLYCOO format, to support that, we introduce a parallel algorithm where this parallel algorithm has no interprocessor dependencies, and it can support element-wise computation of spMTTKRP and a tensor remapping in parallel. So you can hide the remapping cost or the remapping, uh, or you can overlap the tensor remapping time with element-wise computation. To support this parallel algorithm, we introduce an accelerator design where we target FPGAs with multi-superlogic regions, and for in each superlogic region, we introduce a compute unit or operation unit we call an axle. And in each axle, it contains a PE and a memory controller. The PE can execute element-wise computation, and the memory controller can effectively or efficiently load data requested from these PEs, and it can support on-the-fly remapping computation. Since we are targeting multi-SLR based FPGAs, uh, to uh, to support efficient connections or between axles, we introduce a ring-based interconnection between axles, where each axle can communicate with its neighboring two axles. So we distribute these factor matrices or in factor matrices across DDR memory. So these can be accessed by an axle through this ring connection if that um, factor matrix is not reside in on its own DDR. And also we make sure the tensor partitions and the output factor matrix partitions assigned to a processing uh, assigned to a PE is stored directly into its directly connected DDR. So the communication that you required from that ring connection is to load input factor matrices and to support on-the-fly remapping tensor elements. When it comes to the processing engine, each pipeline, so processing engine have multiple pipelines. So each pipeline can perform element-wise computations. And each pipeline has a partial matrix buffer where it keeps partial values and do accumulation within the pipeline. So it avoids the data explosion itself. And in the memory controller, we can divide it into two sub-modules. First one is the cache subsystem, where we use the cache subsystem to explore the data locality of input factor matrices. And we have a DMA or direct memory access buffers to load tensor partitions in a streaming fashion and store factor matrix partition in a streaming fashion back to the FPGA external memory. Also, we have tensor remapping module to support the on-the-fly remapping. And we have an accelerator to communicate with neighboring axles. So it loads input factor matrices and store remap tensor elements, as I discussed before. In our paper, we have performed a thorough theoretical analysis and provide you proofs to show that when it comes to tensor remapping, the total FPGA external memory required to perform on-the-fly remapping is always twice the size of the tensor, no matter how much modes or dimensions the tensor has. And the tensor remapping cost is not the nominant factor of the total execution time. We also provide empirical results on this. And also when it comes to load balancing, computation is load balanced across all the axles in all modes. And tensor data is always available in each PE. Tensor data is always available for each PE in its directly connected external DRAM memory. Moving on to the results. So our target platform is a Xilinx Alveo U250 multi-SLR platform, and we chose 5 tensors from Frost library uh, and to identify the optimum accelerator configuration parameters. We use a performance model simulator, and the chosen configuration is shown in lower right side. And for that particular configuration, the resource consumption is also shown over here. We so that when we increase the number of axles or number of pipelines to increase the DSP utilization or URAM utilization, we saw that the total the maximum frequency that, or the frequency that we can run the accelerator reduces. So the overall performance tend to reduce. So this is the optimum resource consumption for us. And we compare our result with state-of-the-art implementations, mainly Alto, which is introduced by Intel High Performance Computing Lab. And Alto is performed only on CPU. And also Georgia Tech has introduced FLYCOO on CPU and GPU. And MIT is also introduced a implementation called Tahoe, which can support CPU and GPU. And also we have a baseline implementation on COO format. So COO-based CPU and GPU implementation. So we have chosen these baselines, state-of-the-art baselines, to compare with our work, and we name our work as FLYCOO. So and we ran these experiments on the CPU experiments on Intel Xeon Gold 5120, and we ran GPU baselines on NVIDIA RTX 3090 and NVIDIA RTX A6000. So compared to GPUs, our work has improved the total execution time by 3.8x. And compared with CPU, our implementation is faster, 8.8 times faster. And here we have shown the impact of tensor remapping to the total memory access time. You can see that for all the data sets that we consider, it's always under 20%. So in conclusion, we proposed FLYCOO, a novel tensor format that can support on-the-fly tensor remapping. It avoids intermediate values being communicated to the FPGA external memory. It also explores the locality of external memory accesses. Based on FLYCOO, we developed a novel FPGA accelerator design where PEs with multiple pipelines to concurrently process input tensors. And we introduced cache subsystem to exploit the locality of input factor matrices. Also DMA buffers to load tensor partitions in a streaming fashion. Also we custom hardware to support on-the-fly tensor remap. Having these optimizations, our work achieved 8.8x and 3.8x improvement in total execution time compared to state-of-the-art CPU and GPU implementations. This concludes my presentation. Thank you.